This is section 5.2, exponential functions and graphs. Definition, domain, range, and graph. We're going to actually get the domain and range from the graph. We're used to seeing expressions like x cubed or even x to the 1/2, where the base is a variable and the exponent is a number. We're going to switch that now. The base will be a number and the exponent will be a variable. So instead of having something like x cubed, we'd have 3 to the x, or instead of x to the 1/2, we'd have 1/2 to the x. So the definition. Let a be a non-negative real number other than 1. The exponential function base a is given by f of x equals a to the x power. I like to keep a greater than 1, but there is no guarantee that you always have a greater than 1. So again, I like to have a bigger than 1 because we can make certain statements about it. But we need to be prepared for what happens if a is between 0 and 1. Remember, a can't be 0 and a can't be negative. Domain, range, and graph. We'll get the domain and range by looking at some graphs. Okay, we're going to pick some very, very easy numbers, and these are probably as in your book as well. So graph the following. And remember, I like to keep my base bigger than 1, so the easiest number bigger than 1 would be 2. So our first is going to be f of x equal 2 to the x. Okay, now remember, anytime you're trying to graph something other than using your graphing calculator, we just make a little table of values. So I start with x being 0, and 2 to the 0 is 1. So I got 0, 1. Remember, anything to the 0 power is 1. That's kind of an interesting observation. So no matter what the base is, a to the 0 is going to be 1. They're all going to pass through 0, 1. If x is 1, 2 to the first is 2. So I've got 1, 2. Again, don't say it's a line. Remember, we've got to plot enough points to start seeing a nice shape take place. If x is negative 1, 2 to the negative 1 is 1/2. So at negative 1, I'm up here at 1/2. If I try 2, 2 squared is 4. So I'm at 2, 4. Okay, hopefully you see it starting to curve a little bit now. If x is negative 2, 2 to the negative 2, I get 1/4. Now notice, whatever power I take 2 to, it is never going to equal 0. This thing is never going to cross the x-axis. And no matter what power I take 2 to, it's never negative. So this graph is entirely above the x-axis. So I can now draw it. Okay, it doesn't really touch the x-axis, it's just the thickness of the drawing there. Okay, this curve is called exponential growth. Okay, and anything that behaves this way, we say it's growing exponentially. What exponential growth is means in the beginning it doesn't grow very fast, and then all of a sudden it just takes off and grows rapidly. The classic example of things that grow exponentially are what are called populations. The population could be money, people with a disease, or animals with a disease, or a forest fire. Those are examples of populations. My next example is g of x equals 3 to the x. Again, I like to keep my a bigger than 1, so the next easiest number after 2 would be 3. Again, we make a little table of values. If x is 0, 3 to the 0 is 1. Remember, anything to the 0 power other than 0 is 1. They're all passing through 0, 1. If x is 1, I have 3 to the first, which is 3. You notice it's a little bit steeper than our previous graph. If x is negative 1, 3 to the negative 1, I get 1/3. So 1/3 of the way up. If x is 2, I have 3 squared, which is 9, which is way up here. And if x is negative 2, I have 3 to the negative 2, which is 1/9. Again, it's never going to cross the x-axis, and it's always going to be above it. So if I connect the dots here, you get something that looks like that. Now notice, if I didn't have any scales on the axes, this graph and the previous graph would look basically the same. So we're going to get some properties of these curves. So fact, if a is greater than 1, then the graph of y equal a to the x will look like this. Okay? The only thing we know, it passes through 0, 1. Remember, they all pass through 0, 1. So anything that looks like this is an a to the x with a bigger than 1. Remember, there are fractions bigger than 1, like 3/2, 7/5, and so on like that. So if a is bigger than 1, the graph of y equal a to the x will look like this, and you know it passes through 0, 1. Some properties of y equal a to the x for a bigger than 1. Okay, and in these properties we're going to get the domain and the range. Our first one, it passes through the point 0, 1. That actually is a big deal. All the exponential functions pass through 0, 1. We couldn't make that statement about lines, parabolas, or any other type of thing, but for the exponential functions, y equal a to the x, they all pass through 0, 1. Number 2, the domain is all real numbers. Okay, when we were picking our x values, we gave it 0, we gave it positive, we gave it negative. That would be everybody. And remember, if you look at the graph, a to the x was always bigger than 0. In fact, it never equals 0. So the range is 0 to infinity. Okay, it's the open interval from 0 to infinity. Another way of saying it, it is y greater than 0. Okay, so the range is 0 to infinity, or y greater than 0. Number 4, the graph is in one piece. Okay, that may not seem like a big deal, but remember, previously we did have graphs that were not in one piece. Number 5, it is always increasing. Okay, so as you read from left to right, it is always going uphill. Number 6, it passes the horizontal line test, so it has an inverse that is a function. Okay, we'll actually see the inverse in the next section. Number 7, it gets closer and closer to the x-axis, technically the negative x-axis, without ever crossing the x-axis. The x-axis is an asymptote of y equal a to the x. Technically, we would say it's a horizontal asymptote since the x-axis is a horizontal line. The biggies are the first 3, the passing through 0, 1, the domain, and the range. Okay, the graph in one piece, that is called continuous. So the graph of f of x equal a to the x is continuous. The fact that it has inverse, we'll see that in the next section. Okay, back to the examples. We need an example with 0 less than a less than 1. Okay, if we think about what happened with 2 to the x and 3 to the x, all we really need is 1. So an easy fraction between 0 and 1 is going to be 1/2. So our third example is h of x equals 1/2 to the x. Okay, now remember, I like to keep my a bigger than 1. So we're going to rewrite the way 1/2 looks. Okay, 1/2 is 2 to the negative 1. Okay, we actually looked at that way back in chapter R. I have a power to a power that says multiply the exponents. That would be 2 to the negative x. So instead of having a to the x with a between 0 and 1, I'm going to have a to the negative x with a still bigger than 1. So again, all the graphs should look more or less alike when we do these. So we make a little table of values. Now whether you use 1/2 to the x or to the minus x, you're going to get the same values for y. So if x is 0, again, anything to 0 power is 1. So far it looks like the other two that we did. If x is 1, now whether you do it 1/2 to the first or 2 to the negative 1, you get 1/2. Okay, remember, previously the 1/2 was over here. If x is negative 1, okay, 2 to the negative 1, minus minus is plus, so I get 2, negative 1, 2. Hopefully you see something going on with this thing. And again, if you think about our translations, transformations, and reflections from chapter 2, hopefully you realize what's going on here. If x is 2, I get 2 to the negative 2, which is 1/4. And then if x is negative 2, I get 2 to the negative 2, which is 2 squared, which is 4. So the graph is doing this. That is what's called exponential decay. Examples of things that decay exponentially, again, are populations. It's kind of the rate at which a town becomes a ghost town. It's also the rate at which radioactive substances decay. Okay, it never crosses the x-axis, but it does get closer to it. Again, if you think back to chapter 2, this is a reflection of the graph y equal 2 to the x through the y-axis. Fact. If a is greater than 1, then the graph of y equal a to the negative x looks like this. Okay, it passes through 0, 1. Notice it's the reflection through the y-axis of y equal a to the positive x. Okay, now again, this is for a bigger than 1. Notice the exponent has changed sign. That's the difference. Let's get some properties for this. So the properties of y equal a to the minus x for a bigger than 1. We're going to list the properties in the same way that we did the others. So number 1, it passed through the point 0, 1. Number 2, the domain is all real numbers. So far it's the same as y equal a to the positive x for a bigger than 1. The range is still 0 to infinity. Number 4, the graph is in one piece, just like earlier. Number 5, it is always decreasing. That's the only thing that's different. Okay, so as you read y equal a to the minus x for a bigger than 1, as you go from left to right, it is going downhill. Number 6, it passes the horizontal line test, so it has an inverse that is a function. And number 7 gets closer and closer to the x-axis. Again, technically the positive x-axis without ever crossing the x-axis. The x-axis is a horizontal asymptote of y equal a to the minus x. So again, we really care about the first 3. Pass through the point 0, 1, domain is all real numbers, and the range is 0 to 1. Okay, notice the exponential functions do not have an issue with their domain. Their range is what is interesting. Now, when we were graphing these, we picked nice points, but remember, in order to say that it's continuous, that it's in one piece, I had to be able to evaluate a to powers like a to the pi, a to the 2 pi, a to the square root of 7 power, and so on. Classically, to do that, you will need a calculator. So, discrete compound interest. So recall, simple interest is money that money earns over time. Only the initial investment or deposit, called the principal, is allowed to earn interest. The idea of compound interest is after a certain period of time, called the compounding period, the interest is allowed to earn interest. So it's interest on top of interest, which if you have an investment, that's a good thing. If it's a loan, that's a bad thing. So the formulas for discrete compounding. Number one is A is equal to P times 1 plus R over N raised to the NT power. Notice the exponent is a product. When you give it to your calculator for the TI-83 and some of the earlier TI-84s, you need to keep that exponent in parentheses since it does involve an operation. Number two says that's an I. I is equal to A minus P. Where? What do these letters stand for? P is equal to the principal. It's the initial amount. It's the money invested or deposited. It's also called the present value. When called present value, it is usually denoted by PV. If you have a business analyst type calculator, it will sometimes have a key labeled PV. A is a new amount. It's also called the compound amount or future value. When called the future value, it is usually denoted by FV. And again, business calculators will have a key labeled FV. It's also called maturity value, which is sometimes abbreviated as M, as in maturity value. R is interest rate as a decimal number. So 5.6% would have R equals 0.056. On the scientific calculators, anytime you're doing something with a percentage, it must be converted to a decimal number. T is time in years, and N is equal to the number of times per year the money is compounded. So we need to know some numerical values for some of the words that go with N. So these are the formulas that you will need. Okay, it's called discrete because after a certain discrete period of time, like a month, a week, a day, whatever, the interest is allowed to earn interest. We will see a different type of compound interest in a moment. So the values for N, okay, to go with certain words. Okay, remember, N is the number of times you do the compounding. Annually or yearly, N is 1. In 1 year, there is 1 year. Okay, semi-annually, half a year. There are 2 half years in 1 year. Quarterly, there are 4 quarters in a year. Notice there is no word for 3. Monthly, there are 12 months in a year. Weekly, there are 52 weeks in a year. Daily, 365. Okay, we will always use 365 for a value N unless you're specifically told otherwise. Sometimes we use 360. That's usually called a banker's interest or nominal interest. So unless you're told otherwise, use 365 for N. And remember, money is classically rounded to the nearest whole cent. That's 2 places to the right of the decimal point. Occasionally, you'll be told to round to the nearest whole dollar. So read the directions carefully to see which one it is you're supposed to do. Some examples. Unless told otherwise, round all final answers for money problems to the nearest whole cent. Nearest whole cent is 2 places to the right of the decimal point. So on your calculator, you could set your float to 2. Number 1 says, $400 invested at 7% compounded monthly. Find in Part A the new amount in 9 years. Part B the interest earned in 9 years. Now when you're doing the problems, be careful about which one you're finding. Are you finding the amount or are you finding the interest? So for Part A, we're using A is equal to P times 1 plus R over N raised to the NT power. Okay, looking at the problem. $400 is invested. That's P. 7%, that's R. 7%, which is 0.07. Compounded monthly, 12 months in a year, so N is 12. Find the new amount in 9 years, T is 9. So that's what we're plugging in. To do this, of course, you will need a calculator. So let's take out our calculator here. Okay, so I'm looking at 400, open parenthesis, 1 plus 0.07 divided by 12, close parenthesis, raised to. Okay, notice I put parentheses here. Let me go ahead and do it here as well. Open parenthesis, 12 times 9. Now, when you go to the exponent, don't forget to hit the caret key, your power key, and then just press enter. So I'm getting 749.670, so to the nearest whole cent, it's $749.67. Now please, when you put the dollar symbol goes in front of the numbers, not after. Okay, for Part B, the interest earned, okay, the interest is going to be the principal, the amount minus the principal. So I is going to be A minus P, so 749.67 minus 400. You get $349.67 in interest. Okay, since we're stuck with using a formula, the only thing that can change are the numbers that we give the formula. Simple. Okay, here are our keystrokes for Part A. You did the 400, open parenthesis, 1 plus 0.07 divided by 12, close parenthesis, and the caret key. The usual thing that goes wrong is students forget the caret key. Then open parenthesis, 12 times 9, close parenthesis. The reason for the parenthesis is for the older TI-83 and some of the TI-84s, if the exponent has an operation, you must put it in parentheses, otherwise you get unexpected results. And then press enter. Our second example. $860 invested at 6 3/4% compounded daily. Find in Part A the new amount in 3 years. Part B the interest earned in 3 years. Okay, 3/4 is 0.75, so our interest is 6.75. So we're using A is equal to P times 1 plus R over N raised to the NT power. Okay, $860 invested, that's P. That's 6 3/4%, so 6.75 is R, which is 0.0675. Compounded daily, N is 365. Time, 3 years. The new amount, A, is, I don't know. So that's what we're using. Okay, to give it to our calculator. Okay, let me clear that one out. Let me go ahead and set our mode to 2 for our float. That way the calculator can do the rounding for us. Why should we strain our brain around? Okay, then quit that. So I have 860, open parenthesis, 1 plus 0.0675 divided by 365, close, raised to, open, 365 times 3, close, enter. We get $1,053.02. Okay, the interest earned in 3 years is going to be A minus P. So 1,053.02 minus $860, we get $193.02 in interest. Now again, remember on the calculator, don't forget your caret key after you close parenthesis for the calculation. Do not round any intermediate calculations. If you round intermediate calculations, you run the risk of accumulating a round-off error. Now let me set my float back to, let me set my float back to float. Otherwise, when I do something else, I might get unexpected results. Now again, if you were taking something like 2 to the 2 pi power, you would do 2 raised to open, because 2 pi is an operation, 2 second pi close parenthesis. You would get that. Remember, anytime your exponent has some sort of operation on the TI-83 and some of the earlier 84s, you have to put the exponent in parentheses. Otherwise, you would get unexpected results. Part 3, the number E in interest compounded continuously. Remember, way back in Chapter R, when we were classifying our irrational numbers, E was one of the examples of an irrational number. We said we would talk about it later in Chapter 5, so here we are in Chapter 5. So the number E itself, if you look at your calculator keypad, there is a place, or there is a key for E. So again, if I take out the calculator, let me get the 83. Okay, right here in orange is e to the x. On the 84, it would be in blue. Okay, always use this key for taking e to powers. This e is just the number e itself. Okay, now just like pi's approximations, so does e. So imagine investing $1 for 1 year at 100% interest. Notice you're investing $1 for 1 year at 100% interest. You can double the money. So after 1 year, you would have $2. So we let the number of times that we compound increase. We want to know what happens as the number of times that we compound increases. The idea is that the number of times that we increase will go to infinity. So in the compound interest formula, we will have P is 1, remember, $1, R is 1, 100% interest, and T is 1, remember, for 1 year. And N will take on larger and larger values. So we want to know what happens to A under those circumstances. Okay, we have a table. Now, I did the calculations on a calculator, of course, and I did not just set the float to 2. I wanted to see all the numbers. Now, the first few actually are exact. So the name again, the value of N, and what happens to the amount, which remember A is equal to 1 plus 1 over N raised to the N power, because remember we had $1 invested at 100% interest for 1 year. Okay, so if we compound it annually, N would be 1. If you actually do the calculation, you're going to get 2. Remember, we could double the money semi-annually. N is 2. If you plug in 2 for N, you get exactly $2.25. Sometimes we can more than double our money. Remember, there was no word for 3. Quarterly. Okay, N is 4. If you plug in 4 for N, you actually get this, 2.44140.625. That one also turns out to be exact. But notice as money, it's only $2.44. Monthly. There are 12 months in a year. When you plug it in as 12, you get 2.61303529022. As money, it's only $2.61. Notice the increase is getting a little bit smaller. This was a 25-cent increase. This was a 19-cent increase. This is only a 17-cent increase. Weekly. There are 52 weeks in a year. Remember, at the end of each week, the interest is allowed to earn interest. You get this value, 2.692596954444. As money, only $2.69. Notice as money, it's only an 8-cent increase. Daily. Remember, 365 days in a year. You get 2.71456748202. As money, only $2.71. Notice it's only a 2-cent increase from the previous amount. Okay, if we went to second or daily, hourly, there are 8,760 hours in a year. You get this value. Notice if I don't do any rounding, they're now agreeing at 2 places to the right of the decimal point. As money, that's only $2.72, so a whopping 1-cent increase. Okay, if I go to minutely, so at the end of each minute, my interest is allowed to earn interest. There are 525,600 minutes in a year. You get this value. Notice, without rounding, they now agree to 3 places to the right of the decimal point. But notice, as money, no change in the amount. It's still only $2.72. If we go to secondly, there are 31,536,000 seconds in a year. So at the end of each second, your interest is allowed to earn interest. Notice, I now have 4-place agreement. And if I round, that would also be an 8. Notice this number appears to be getting closer and closer to something like looks like 2.71828 something. And notice if I round to 2 decimal places for money, it's 2.72. So the value of N is getting larger, it's going to infinity, and this column is approaching some number which is actually less than 2.72. So this goes to infinity, this column goes to the number E. Okay, so E is about 2.71828 and a bunch of other stuff. So E is about 2.71828, 1828, 45, 90, 45, and so on. It's irrational. Always use your calculator's built-in value for E. Always use that e to the x key, which is actually the second of the ln key. So approximate the following. Round your final answer to the 6th place or right of the decimal point. Okay, since we're going to need our calculator, let's go ahead and take it out. Okay, our float we should set to 6. Whoops, too far. We're going to set our float to 6. So mode, float on over to 6, press enter, okay, and then quit. Okay, here's our first one, e to the negative 1.429. So on your calculator, do second e to the x. And notice it's already open a parenthesis, it already has the caret key. On the 84s, let me go ahead and drag this one out. If you do your second e to the x, notice you're already in the exponent. So if I do my negative 1.429, close parenthesis, you get 0.239548. Number 2, okay, no, here are your keystrokes. You're going to do second, your e to the x ln key, negative 1.429, close parenthesis. Remember the 83 opened it, the newer 84s don't. You're up in the exponent, and then press enter. Number 2, e to the 1.094. Okay, if you do the exact same thing, second, ln, 1.094, close, enter, 2.986195. Number 3, 1278 times e to the 1.038. Again, on the calculators, you can do it exactly like it looks. Let me clear this out. So 1278 second ln 1.038, close your parenthesis, press enter. You get 3,608.515092. Okay, now remember, all this came about because we were investing $1 for 1 year at 100% interest. Notice we were letting the number of times we compound go to infinity, which means we were having smaller and smaller amounts of time before the interest was allowed to earn interest. So interest compounded continuously. Number E came about by increasing the number of times per year that we compound the interest. So it's kind of like we were trying to compound every time we looked at our money, not just at the end of each second or at the end of each tenth of a second or at the end of each thousandth of a second, but no matter when you looked at your money was earning, your interest was earning interest. So if the interest is always being compounded, called continuous compounding, we have the following formula for the new amount. A is equal to PE e to the RT. Okay, and I, the interest earned, is still A minus P, so that's P times e to the RT. Okay, to use this formula, you actually see the word continuous or continuously in the problem. If you see any of the other LY words, weekly, daily, yearly, and so on, that's the discrete compound interest formula. This is the continuous compound interest formula. Notice it's fewer keystrokes for you. So, some examples. We're still going to round our final answer to the nearest whole cent, which is 2 places to the right of the decimal point. Remember, it's money. So, $600 invested at 6.29%, compounded continuously. Find the new amount and interest earned after 8 years. Okay, there's no part A and B, but it's still 2 questions. So I see the word continuously. So I'm going to use A is equal to P e to the RT. Okay, $600 invested, that's P. 6.29%, that's R. So 0.0629. Okay, compounded continuously, that's taken care of in the formula. T is 8. New amount is, I don't know. So we're using 670 times E raised to 0.0629 times 8. If we take out the calculator, okay, let me clear that. Let me set my mode to 2. So setting my float to 2 for money. Okay, so I've got 670 second e to the x 0.0629 times 8, close parenthesis. I'm getting $1,108.18. Okay, remember, do not round, enter any intermediate calculations. So $1,108.18. Okay, remember the interest earned, it's A minus P. So 1108.18 minus 670, we have earned $438.18. Now, kind of as a built-in check, A should always be greater than P. Always, 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 always. The new amount is always greater than the principal whenever you're doing the money problems. So let's take a look at one more. I mean, they can't be radically different. We're forced to use formula. Number 2 says, $900 invested at 7.99%, compounded continuously for 14 years. Find the new amount and interest earned. So again, I see the word continuously. So I'm using A is equal to P e to the RT. $900 invested, so P is 900. Rate 7.99%, so 0.0799. Time 14 years. So I'm looking at A is I don't know. So A will be 900 times e to the 0.0799 times 14. So when you take out the calculator, clear that. 900 second ln 0.0799 times 14, close parenthesis, $2,754.51. Now again, when you put the dollar sign, it does go in front of the number, and there is no space between the dollar sign and the number. I know we say dollars after, but the dollar sign goes in front. Okay, the interest earned is going to be A minus P. So $2,754.51 minus 900, you get $1,854.51. Again, when you're doing the problems, usually it's only one or the other. It's either the new amount or the interest earned. When you do the problem, read the problem carefully as to which one you're supposed to be finding. Do not answer too much. Do not answer too little. If you're only asked to give the new amount and you give the new amount and the interest earned, it will be marked wrong. Only answer what you're being asked. Do not answer more. Do not answer less. That's the end of section 5.2.